We good? Okay, let's do an example here. M2. Okay, so the first step was draw the picture. So you draw the picture and label things symbolically. We get to assume all sorts of good stuff, like the string doesn't stretch, that the string has negligible mass, the pulley has negligible mass, and negligible friction. So now we're supposed to solve for the motion of the two masses. Yes, please.
Is there a friction on the plane?
No friction on the plane. We'll get to friction later. Okay? No friction on the plane. So first, before solving the problem, tell me what will happen.
Well, it depends on if mass 2 is
Who's bigger? It looks like M1 is bigger.
In which case, M2 is going to go up and M1 is going to slide down.
So it seems to me there are three choices. What are the three possibilities?
Nothing happens.
Nothing happens. We release it from rest and they just sit there. Okay, they're in perfect balance. Okay, that's one possibility.
M2 goes up, M1.
Okay, another possibility would be that M2 goes up when M1 comes down, and the third one is the opposite, where M2 goes down and M1 goes up. How can I solve the problem if I don't know which one of those is going to happen?
Just keep them symbolic.
Yeah, just keep it symbolic. Mark very clearly what direction things are that I'm assuming we're taking as positive. And then if I end up with a negative acceleration, it means, it was going the other way. Okay? So, what would you like to isolate here?
M1.
You want to do M2 first?
Fine, we'll do M2 first.
Let's do M2 first. It looks easier to me. So I isolate M2. Here it is. What are the forces on M2? Gravity. Always remember to put gravity in if gravity is there. Anything else? Tension. Okay, tension going up, being applied up there. So you're probably getting the idea. I'm going to try to represent each object in its about appropriate shape and orientation and try to apply the forces on the diagram where they actually are applied. So gravity is a body force. It's applied throughout, so we'll put it at the center. Okay, any other forces on 2? We're good. Okay, so now next step. I need to define a coordinate system or pick a direction for acceleration. What is your choice? Down or up? Down? Down with acceleration. All right, so we're going to pick down as the direction, and I'm going to, this is mass 2, so I'll say acceleration 2 going down that way. Okay, so having isolated this object, I now apply that the sum of the forces is equal to the mass times the acceleration. Sum of the forces in the direction I've chosen as positive for the acceleration would be m2g minus t is equal to m2a2. Okay, so that's one equation. I'm going to bless that with the number 1. We're going to keep track very carefully of the number of equations and the number of unknowns because we know once we have the same number of equations as unknowns, we can solve. Okay, how many unknowns are there in this equation? How many quantities are not effectively given to us? Namely, we don't know the tension and we don't know the acceleration. So if we only have one equation and two unknowns, we can't solve. So we need to keep looking. What do I isolate next? M1. So I'm going to isolate M1. And what are the forces on M1? Gravity again. There is a normal force from the inclined plane that is keeping mass 1 from falling straight down. And the direction of the normal force is normal to the interface. That is perpendicular to the interface. So up it comes this way. And we'll call that N. Anything else? Tension. Okay, now, is it legal for me to call that tension T?
Yes.
Why? What justifies my calling this tension T? So, if the string were to stretch, I couldn't get away with that. What else? If the string has mass, if the pulley has mass, if there's friction around the at the axle of the pulley, that would screw this up. But if I were to analyze the pulley now and say, okay, it has a tension force T1 on this side, and it has a tension force T2 on that side, but the pulley has no mass. If T1 is not equal to T2, then the pulley will accelerate infinitely. So we need that the tensions balance around there. So I am justified, because of all the assumptions that I'm allowed to make, to say that the tension here is the same as the tension there. Any other forces? Ugh, this one looks more complicated. How am I going to, second step, I need to pick a coordinate system. What do you propose? Tipped with the angle theta? What would be an advantage in picking a coordinate system that's tipped like the plane? Yeah, the acceleration is only going to be along the plane, and so I won't have anything interesting happening in the orthogonal direction, so that will probably simplify my life. So I'm going to pick positive for acceleration A1. You got to be careful here. Now, I don't want to pick that way. That would be bad. So I'll pick an XY kind of coordinate system that's tipped that way, so that I can now resolve the coordinates in the X direction and the Y direction. Okay, so the sum of the forces in the X direction must be equal to m1 times the acceleration of 1 in the X direction. And then we'll do the same thing in the Y. What is I need the sum of the forces. So what is the contribution from N to the force in the X direction? Nothing, because it's perpendicular. What about T? All of it, right? Okay, so I have T. Now what about M1G? It's only a part of M1G that I need. So in this picture of M1G, I'm going to build up I've got to be careful and build this up in the right way. I'm going to build up the force M1G with a part that is parallel to the x-axis plus a part that is parallel to the y-axis. And so this is going to be a right angle here. Okay? So this would be the x component. And this will be the y component. And then where is my angle theta? So this direction makes angle theta. So this angle here is what? Is that the is that called complement? The 90 degrees minus theta would be this angle. So what is this angle? Theta. That's back to theta. Okay, so I need to know this component. How much is that compared to the hypotenuse? That is that's the opposite. That's the far side over the hypotenuse. So I have minus m1g sine theta. Now, a way I like to check these things is to pretend that the angle goes to some convenient value. So let's pretend the angle theta goes to 0. Okay, imagine that theta is 0. So this is collapsed down and is horizontal. So in that case, this predicts that I should have no component of the force. Is that correct?
Yeah, it's frictional.
Because gravity is straight down, and I'm analyzing along that horizontal direction, and those are perpendicular. So I think I should be happy with sine, because sine of 0 is 0. Okay? Equals m1 ax. So there's another equation. Sum of the forces in the y direction is equal to m1 a sub y. Why is this one not so interesting? What would I learn from doing this one?
Nothing.
I would learn something. Yeah, I would learn how much normal force needs to be in place to counteract the component of gravity that is perpendicular to the plane. So it won't affect the motion. So I don't, strictly speaking, need to worry about it. I know that the acceleration in the y is going to be 0, but just for practice, let's do it anyway. I have y is positive that way, so I have n. And then I'm going to need a component of gravity. But now the component of gravity that's along the normal is this one. And that's the adjacent side, so this is going to be cosine. And there will be no acceleration. Why? Because the normal force n will adjust itself to be just enough to balance gravity so that the block doesn't fall through the incline. So that would be a third equation, and that would allow us to figure out the normal force. Okay, so it's time to reckon a little bit. How are we doing in terms of numbers of equations and numbers of unknowns? So the unknowns, what's unknown? T. What else? Okay, I have A2. I have AX. And in principle, I had N. So 3 equations, 4 unknowns. How come I'm still confused? Say again? Okay, if the string doesn't stretch, then the acceleration of mass m1 up in magnitude has to be equal to the magnitude of the acceleration of a2 down, and vice versa. They can go either way. So since if the string is inextensible, therefore A2 is equal to AX. And now we can solve. Please.
That's only true if you're careful to define your direction of motion so that A is positive for one direction of motion of the string.
So I almost screwed this up, but it's worth making the point. If I have defined, as you can see on the top isolation diagram for M2, that the direction I'm taking is positive for the acceleration A2 is down. If that is positive, if M2 falls down, then M1 must go up. And so I have oriented the coordinate system for 1 to be in agreement. Positive is going up. Do I have to do that? What if I was perverse and I did it backwards? Yeah, so then when I came to this line, they would have to be opposite because I had chosen an opposite direction for AX. And when one was positive, the other then would have to be negative. So I need to look carefully at the way I've chosen my directions in order to decide whether they should be positive or negative there. Okay, so I now have basically to use equations 1 and 2. And I see something nice. I see on the top equation a negative t. I see a positive t in the second equation. So if I were to add those two equations together, t would disappear. So I'm going to add 1 and 2. And when I do that, I get M2g. The t's go out, minus M1 g sine theta must be equal to M2. I'm now going to say both of them are the same. We made that assumption. So A2, if you like, plus M1 AX, which I'm going to call A2 because we have that equation as well. So the right-hand side is M1 plus M2 times the acceleration, A2. The left-hand side, I suppose I could factor out a common factor of g. So I have M2 minus M1 sine theta, g. And so dividing through by the sum of the masses, I get that the acceleration A2 is equal to M2 minus M1 sine theta over M1 plus M2, all of that, times the acceleration due to gravity. Okay, so there was a lot of algebra, and it's worth checking to see if this makes sense. What does this imply when theta goes to 0? Theta goes to 0, then the wedge is no longer a wedge, it's just the table. So we have a mass M1 on the top of the table and a mass 2 falling down. This term drops, and we have M2g is the incentive to go down, but how much mass is moving? All of it, M1 plus M2, and so the acceleration that we're going to get is the net downward force, M2g, divided by all the mass that's being accelerated, M1 plus M2. Does that make sense? We good? Okay, so that checks out. Dimensionally, this stuff, it's a ratio of masses, so that's dimensionless, and therefore we get the acceleration is g, proportional to g, and that's good too. Yeah, Bonnie?
I was wondering why it doesn't matter that our coordinate system for M1 is posted, but our coordinate system is posted.
Right, so you have this freedom. Notice I I used an xy. I suppose I could have said x1 and y1 and used those coordinates for mass 1, and I can use different coordinates for mass 2 as long as I link them together in the appropriate way. And the linkage happened right here. Right? Okay? So the distance that mass 1 moves up bears what relation to the distance that mass 2 moves down? So if mass 1 moved up by 5 centimeters, how far down would mass 1, sorry, if mass 1 moved up by 5 centimeters, how far down would mass 2 move? If the string doesn't stretch, would it be the same? Yeah, so it would be the same. So if you like, I have an x1, x1 going up that way. I have an x2 going down this way. And any change dx1 must be equal to the change dx2. So if that change happens in a time dt, that says that v1 must be equal to v2. And then I can differentiate again and get a1 is equal to a2, which is what I ended up using. So that was a great question. Okay.